Moving on to our next talk, Job Scheduling in Hadoop, an expose by Joydeep Sensarma Co-founder Qubole.
Okay, friends, my name is Joydeep, and thanks for having me back. I was here last year as well on one of the panels, so hopefully I did a decent job, so they called me back. So I'll just give you a background on why I'm here. Raghu was one of your principal architects, called me maybe a month back and said, hey Joydeep, what is this Hadoop 2, this yarn thing? Can you tell me something about job scheduling? And I was like, man, like that is like Ramayana and Mahabharata, you know, like you want me to tell you over the phone, like about this topic? And it was like, why don't you come to this conference and, talk about it? So here I am. And we were both, talking about how to name this talk. And I told him, look, it's the political sort of the climate is to do exposés these days. So, I'm trying to do an expose of Hadoop. As is usual, I only made these slides yesterday night. And I realized that I will not be able to talk about the entire topic because it's really a Mahabharata. So I'll try to stick to things that are, I think, a little bit different. There's a lot of stuff about Hadoop on the net. You can go to SlideShare. There are tons of presentations. I'll try to give you something that is a little bit of what I have done and a little bit more that is born out of my operational expertise in this area, and something that hopefully is not a repeat of something that's already out there. All right, so here's a little bit about me. I started in Facebook in about 2007. I bought up the Hadoop clusters, and over the course of the next 4 years, I spent roughly 3 years actually in charge of those clusters. So as we scaled from 100 terabytes to like some 30, 50 terabytes, and gazillion numbers of users, jobs, whatever. In the meantime, I wrote Hive. I did a bunch of stuff around HBase. One of the things that's very relevant for this talk was that I was mentoring the person who wrote the Hadoop Fair Scheduler, sort of PM/mentor for that project. Even though I was a service provider within my company, I was also actually a user. So I floated around different teams and actually went to the payments team. So I kind of did, the kind of stuff that a lot of people here do in Flipkart. So on the Facebook credit stuff. And I actually used the systems that I had built and run myself as a consumer. And so I got a little bit of the perspective firsthand of what that felt like. With respect to, again, the topic at hand, I've spent a lot of time actually looking, debugging endless problems and sort of, actually rewritten fairly large parts of the Hadoop source code, some of it which was inside Facebook, not everything was open source. And I'll talk about this project, Corona, quite a bit, in which I started and did quite a bit of stuff. Since the last couple of years, I've been sort of at this company called Qubole, and I think we are definitely having some of the largest Hadoop clusters in AWS. So I'll try at the end to sort of go a little bit towards, directionally, what are the new things that I see happening in this part of the world. All right. So before I start the talk, I realized that the previous talk that we did about the Promise engine, funnily enough, there's so many overlap between that talk and this talk, and it's just amazing. The world is like a fractal. Like I'm going to talk about a very low-level system of running parallel map-reduce jobs and so on, and these guys are talking about fulfillment and retailers and stuff, and you'll see some of the analogs of these two systems come through, which is kind of amazing. All right, so this is the expose. Like, what crime did we commit? And I love this. I love this picture. This is a saying, the family that craps together stays together. And the root of it is the fact that in a company like Facebook or at Flipkart, you're almost forced to have these really gigantic compute clusters. And I've tried to list some of the main reasons, right? The one is that obviously statistical multiplexing. And you get sort of lots of users who are active at one time but not at the other, and you get some other users who are active at some other time and not at the previous time. And you can multiplex all of these workloads into a common shared compute pool and just get sort of the benefits of statistical multiplexing. The other huge reason is that like any madly growing company with like massive amounts of data, we never had enough hardware, and so we the only way we could run some of our largest jobs, typically from the advertisement business, was to actually run them on all the hardware that we had at that point. So for a very long time period, we were forced to just, by virtue of this fact, have really large clusters. Another really nice advantage, with respect to MapReduce. So I'm not going into a lot of detail about, what MapReduce is and stuff. I kind of hope that, a lot of people out here know that already. So you know that, there's, data locality, right, which is fairly fundamental to MapReduce. So we used to throw all of our data into a common Hadoop cluster, and if all of your jobs were running on the same hardware, then you would have a good chance of placing your compute tasks close to the data nodes on which the data was placed. Of course, as a service provider, we had a small team of about 10 or so for a very long time. It was just so much easier to manage 1 or 2 clusters. But other than all these really sound, rational reasons, at the gut of it, I somehow believed that the family that traps together stays together. And for the long time, I kept fighting that, we should not have multiple clusters, because I felt that, even though it was a hard problem, that the benefits exceeded, the pain that we had to incur to solve the problems. And this is sort of I was thinking, so I realized while preparing this talk that I've been working on Hadoop from 2007 to 2014. So I myself have become like a batch computing node, like working on Hadoop forever. But this is sort of, all the problems that I remember seeing. So back in 2007, this is a really long time back. It's like prehistoric. When we first bought up the clusters, there would be like, rage wars going on between like analysts. Kind of like the road rage we see in Bangalore. People would just say, "Are you freaking crazy? Like, this is a first in, first out system, and you've submitted a job with like 30,000 reducers, and we have like 1,000 reduce slots. Like, you're gonna run for the next 2 days." And so we started getting these, this term Hadoop etiquette. Do you have Hadoop etiquette or not? And we did a bunch of like really simple things. That was a long time back. I said, okay, you can't have more than some number of reducers. The problems kept changing as we kept evolving. We had so many instances where people would take down the cluster. The standard thing is some guy comes along, says, I'm going to put like billions of rows in a Python dictionary. That can't possibly go wrong. And he would take down the entire cluster because everything would go out of memory. So simple problems, got rid of this problem. Then this problem started getting sophisticated. Now, we prevented people from bringing down things, but they would still make things really, really slow. So somebody would come along and write a job that populated millions of files. So essentially they are creating files as fast as their code can run. And we have one Hadoop node and the name node, and nobody else can create files. And it's like everybody's thinking like, what's going wrong? There's no CPU utilization, nothing, nothing's really visible in the system, but everything is stored. Right, and so we had like things like that, denial of service, essentially internal denial of service attacks. The more success we got, so 2010, I recollect, again the problem changed. I can't even get into the RAM cluster. It's so hot, it's so busy that forget about getting a good CPU slice. I can't submit my job, my Hive query to the cluster. Then we kept innovating. We said, okay, we'll do fair share, we'll do quotas, we'll do this, that. And we did a bunch of stuff around fair scheduling, which I'll just quickly cover. And then these people started coming and saying that, well, because everybody still needs more compute than we have. And they are saying, you guys say that you are doing fair scheduling, but how do I know? Prove it to me that you gave me my quota of the cluster. It's like, how do I prove that? Look, here's the dashboard, here's like 50 users, and like you got like 10, and like, no, you got to give me a proof. So an interesting experience in, I guess, especially for systems people like myself, on being transparent to users and sort of, telling them, how the system works. And I'm still struggling with these problems. So 2013, I'm still at Qubole, still running Hadoop clusters and getting old. And I still see like too many reducers, too few reducers, cluster idle. So I'll talk a little bit about, what we are doing today. All right, so actually, let me just jump. All right. Let's go back. All right, so, okay, so the perfect weapon, right, that looked pretty good. I just did a Google search, it looked like a very nice machine gun. That's the kind of gun I would have wanted. So here are some of the attributes of, here are all the things that the scheduler needs to get right? It needs to be efficient. That means that I've got 1,000 nodes with, some number of gigaflops each, and I want to extract each and every gigaflop out of those machines, right? I want to be scalable. Obviously, I want to be be able to add machines to this pool of machines, as many of them as possible. I want to run scale in terms of the number of users. I want to scale in terms of the number of jobs, and so on. Isolation. I want to prevent one bad user from affecting other users. Right? I want to make it appear to a department, like your supply chain department, that they are the exclusive owners of 1/5 of this cluster, right? Even though they are actually sharing this cluster with 5 other teams. At the same time, when possible, I would like to sort of do a fair distribution of sort of the available capacity across different users. Fault tolerant, obviously, one aspect is simply what Hadoop does very well is just sort of bad machines and stuff, but also sort of transient failures, sort of bad jobs, bad tasks, there's all kinds of faults happening in the system, and your system should never sort of like fall apart. And finally, probably the most important thing for which Hadoop gets dinged a lot is that I want to do all of this stuff while maintaining a responsive system. So actually, many of these goals are actually they are against each other. So for example, a first in first out scheduler is very efficient, but it's actually not fair at all. And when you try to take something like a first in first out system and you try to bring fairness, modify it to bring fairness into the equation, you start sort of running too many things at the same time. You start context switching and stuff, and you get less and less efficient. So there are some inherent contradictions at the heart of this that make this a very hard problem. So like I said, I was not going to be able to cover everything in this talk. So here's the things that we spent a lot of time on that I'll just quickly run through and just not talk a lot. So fair scheduler, the Hadoop fair scheduler, the capacity scheduler was written sometime around in 2008 or 2009. There's been a long evolution path there. There's a lot of stuff out there on the web, but the crux of the matter is that today it kind of it's almost done, I think. And what this allows us to do is it allows us to solve more or less the fairness and the isolation problem, where different teams can sort of cooperatively share a cluster and think that they have some fraction of the capacity. Even though speculation was something that the Google paper, original MapReduce paper mentioned many years back, it took a long time for open source Hadoop. Actually, I'm still not sure open source Hadoop actually has it right. But it's a very tricky topic, and it's extremely critical to your perception of Hadoop as something that works. And if you are an operator or an author or something, that's something that you should look out for. We spent a lot of time tuning and fixing that. Preemption. I'll spend a lot of time on this talk talking about preemption. So almost all fair systems are preemptible, right? So we are all used to using these Linux, Mac, Windows, operating systems, and obviously, they have preemption, because as we log in and we launch up the UI, the UI goes ahead and displaces work that the computer might have been doing on something else while I was not there, right? And so this ability to stop working on less important things and start working on more important things is, a very important characteristic of any responsive system. And so preemption was added to Hadoop, but it's not really a preemptible system, and so we'll talk about that a little bit, but it's something that, we spent some time adding into Hadoop. And the fourth, things that you guys are intimately familiar with, when you have a high concurrency, high load system, you got to have make yourself foolproof against denial of service attacks at every level, right? Do I have too many jobs in the system? Do I have too many tasks in the system? Am I using too much memory in the system? Am I having a bad actor which is creating too many files in the system? And so we, with very many bad sort of experiences, we kept sort of ticking these off one by one and clamping down the gates. And again, I think we're kind of more or less sort of done with it, at least in terms of the resources that we know are contended for. Okay, so what is this talk about? These are the problems that are still sort of, kind of getting solved. Some of them have been solved by Hadoop 2, some of them are solved by Karuna, some of the things that we have been working on internally. And so this is what I wanted to sort of focus on for this talk, right? So before I do that, let me just actually go through the only animation I have here. So for those of you who don't look at Hadoop on a daily basis, but even those who do, quick refresher, right? How does Hadoop scheduling work? ignore the title. So, somebody comes along, writes a query or a MapReduce job and queues it into the system. That creates lots and lots of small pieces of work, map tasks and reduce tasks that sit around in internal queues. There are lots of slave machines. So, even though this picture is showing one master and one slave, there are actually probably in your systems, the ones that you have deployed, probably thousands of slaves. So the slaves come around at some point and say, hey, I'm live, give me something to do. The master says, okay, here, go take this piece of work, go get it done. Hadoop, for reasons of isolation, has always had a architecture in which most of the work is done by child processes. So not in the, so it's not a multi-threaded large server where threads will do the work, but it actually spawns a child process. So, in response to this task, it'll spawn a child process, and the child process will go do something, come back to the task tracker and say, I'm done. And the task tracker will say, I'm done, I got this thing done. And the master will say, okay, take the next one. Right? So basically, that's sort of the message flow. And now imagine that, you've got 4,000 nodes doing this, blip, 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 continuously, right? At the frequency of, every machine might be churning around a few tasks a minute, right? You multiply by that by thousands of nodes, right? So why did I go through this picture first? To get some context into these critiques, right? And what are the critiques? The critiques is that, first of all, in the picture I showed you, there was a single master node, which is doing the work of scheduling jobs from like hundreds or thousands of users, and scheduling like hundreds of thousands of jobs with millions of tasks, right? So obviously it has a hard time keeping up, and it's also a single point of failure. The second thing, which is why that slide had the title which it had, was that it's a pull-based architecture. So every node that comes along says, hey, give me something, give me something, give me something, right? And again, I know a lot of you guys must know this by heart. Polling-based architectures are fundamentally almost evil. And there's some good things about them, and maybe I'll come to them later on. But basically, the poll-based architecture in Hadoop puts scalability and low latency at permanent war. If you want a low latency system, you would like to poll aggressively. If you want a scalable system, you can't have thousands and thousands of nodes polling at increasingly fast rates. So you've got to throttle back and poll at lower frequencies, right? So everybody kind of has read these, the 10K requests per second server and even D and all that stuff, right? So this is kind of the Hadoop, sort of the Hadoop world's equivalent of that whole debate around, event-driven architectures. The other reason why poll-based is bad, which is not related to the event-driven architecture, is that it simply leaves idle time on the wire, right? So if I come to you and say, give me work, by the time you respond, I have spent 5 minutes of my time doing nothing, right? So it's better that the system, if you want a maximum efficiency, it should always have some work for everybody to do. Third thing is slot-based scheduling. So historically, Hadoop has always divided its available resources into map and reduce slots, and that has some issues there. I'll talk a little bit about pessimistic locking. I think you guys will hopefully find this interesting. And again, this goes back to the reservation concept that actually was being talked about in the previous talk in a very, very different context. So basically, the job tracker has one big lock, and it just brings everything to a stall. And the final, the most intractable problem of all of these that I think still not been solved is that the crux of the problem is this non-preemptibility of Hadoop tasks and the fact that some of them are very, very long running. And this makes it very difficult to build a system that is fundamentally responsive and fair and efficient at the same time. All right, so I'll go into some of these in detail. See, so we've already seen this picture. So let's go past this one. And pessimistic locking. Okay, so bear with me, try and go through this code if you can see it. So every, the process heartbeat. So if you look at the Hadoop code base, hopefully you'll find something like this that looks like this somewhere. So these 5,000 nodes, each one of them heartbeating every, 10 seconds, 2 seconds, whatever, right? Go into this job tracker and say, hey, give me something, right? For a long time, and I believe that's probably still true, the way it worked in Hadoop land is you had the equivalent of a global lock. Said, oh, I need to find something for this guy to do. I've got these millions of tasks that I could choose from. But you know what? I'm going to freeze everything so that I'm sure I get the right thing and I don't corrupt any data structures. So you get this big global lock, and then it does the stuff, and the stuff it does is I just try to simplify, but basically it walks like tons of data structures. It has some priority queues and stuff. At the end of the day, it has to do a lot of hard work, go across lots of linked lists, maps, this, that, and find something that is best for this node to do. The reason it's so complicated is because we are trying to do all these things, right? We're trying to be fair, we're trying to get data locality, we are trying to make sure there's no denial of service attack, and so on and so forth, right? So we got to do a fair amount of stuff in every one of these heartbeats to make sure our system satisfies some of the other properties that we want of it. All right, so I'm going to come back with how this work can be made better, and what we have done, what I know about how this can be made better. All right, so this is the other the second this problem that I want to go in a little bit deeper into, slot-based scheduling. So like I said, Hadoop takes a pool of compute resources, says, okay, I'm going to divide it into map slots and reduce slots. Right? And there were good reasons for doing that. So let's look at what the problem is, right? So let's say I have 8 CPUs, right? And I've got to divide this into map and reduce slots. So I'm like, okay, fine, let's give 4 and 4, right? What's the problem? The problem is sometimes I have too many reducers and no mappers, and I'm like 50% of the CPUs are idle, and sometimes I have too many mappers and not enough reducers, and then I'm raving mad that my mappers are not getting CPU. But if I overcommit the system, if I say, okay, fine, let's just run 8 mappers and 8 reducers, then Hadoop is also very memory intensive, and it wants, like, roughly speaking, at least a gig per task, per slot, right? So now I need these fairly fat machines with, a pretty high ratio of memory to CPU, right? And that's one of the lessons of being in the cloud, is that we have customers that use all kinds of crazy machine types. So it turns out C1.xlarge is an Amazon machine type, which is widely abundant in the spot instance marketplace that our customers love, which has 8 CPUs and only 7 gigs, right? So my last, n equals m equals r theory just goes out of the window, because I have no way I can oversubscribe their slots to consume all the CPU available. So this is my sort of problems I'm dealing with today. So the other sort of main characteristic about Hadoop is that you can oversubscribe CPU, you can oversubscribe network, but you cannot oversubscribe memory, because if you oversubscribe memory, your box will either swap or it will just come crashing down. This whole division is bad. We know that pretty much every computing system that has a hard division, if you make it a soft division, it's better. The other problem is that the reduced task, the definition of the reduced task itself is very, very problematic. So the reduced tasks do nothing in the beginning. They just sit there and say, hey, mapper, give me something. Hey, mapper, give me something, right? And we should go into a little bit into that if possible. They're terrible at what they do. But they just sit there and poll and do network I/O. Once they've done all the network I/O, then they become monsters. They start chewing tons of memory and CPU. So it's a very difficult unit of activity to schedule, because you do not have the ability to move it around. But at the same time, the characteristic of this task changes from being almost purely network I/O to almost purely CPU and memory. Third one, again, so I'm talking a lot about reducers. I think I've been living reducers for the last 7 years, I guess. So let's just jump to the second point. In order for us to sort of get the maximum efficiency possible, since it's an online scheduling problem, I do not know what's going to happen in the future. So when I see a heartbeat, I say, okay, I'm just going to give you whatever is there, right? Because I could have done a better offline scheduling, right? If I have a manufacturing floor and I know exactly what the inventory is and what the work is, I can do this nice offline optimization problems, right? I can solve those problems, and I can come up with a plan, right? But this is not an offline optimization problem. This is an online one where the consumers of resources are dynamic and changing every second, every minute. And to some extent, even the providers of the resources are too, right? So greedy scheduling, right? So we just sort of say, okay, fine, I'll just find whatever the best thing I have for you, and I'll just give it to you. And if things go wrong, then in future, for example, somebody much higher priority comes along, maybe Sachin comes along and wants a report that just needs to be had tomorrow. I'm gonna preempt whatever I gave out previously and switch to Sachin's job, right? So preemption is very, very fundamental to fairness and responsiveness. But the problem is that with this whole artifact of having very long running reduced tasks, there is no true preemption in the system. Every time you preempt something, you actually reset it back all the way to 0. Very much unlike your operating system, which you have on your laptop, right? Preemption is desirable but very wasteful, and there is really no way in such a system to use like short bursts of CPU. So this is a huge problem in this system. All right, so now how can you fix some of these problems, and I'll try to go into who's done what, right? So let's go back to that whole process heartbeat. How do I give you a task, the best task for you without locking up the whole system? And this is like a fairly standard pattern that a lot of you must have seen in databases, in applications, in actually the soft reservation stuff that the previous presentation talked about. The way you do this is say that, look, I'm not going to get a global lock. I'm going to walk my data structures and come up with some candidates. So I need one task for you. I'm going to try and come up with 5 that look roughly good enough, right? Then I'm going to go around and then I'm going to get the lock, and I'm going to try and remove these 5 things from my system to give it out to one of the slave nodes, right? And so this is sort of what this slide is trying to show, is that while you are doing your optimistic sort of walking of all the data structures, you can just sort of get like very localized, fine-grained locks. You don't stop other people, and that's where you spend the most of your time. By the time you figured out your candidates, you've done most of the hard work, and then you just want to remove them from the system. And at that point, you can do a check that says within this global lock, you can say, oh, does this thing even exist? Because maybe while I was I was thinking it's a candidate and I was thinking it's a good candidate to give out, maybe somebody else came and actually grabbed it, right? So the simplest thing that you might do in acquire tasks is to say that let me at least make sure that every one of these tasks still exists as something that's not running in the system, something that needs to be scheduled, right? So a pattern that I've seen many times, in payment systems, Facebook did exactly the same thing. They had hot wallets, and we had to do sort of these soft reservations and hard sort of two-phase kind of stuff. We did this in Hadoop 1 actually. So the Facebook distribution of Hadoop has a job tracker which has a little bit of this pattern. We rewrote most of the code in the job tracker locking hierarchy to get it closer to this pattern, but not exactly. But especially in the Corona project, we from the start said that we are going to build a server that is based around the optimistic locking pattern, and everything is sort of written that way. It's actually not that easy. It's very hard, unfortunately hard, because you have to worry about memory barriers and stuff, because you could be looking at stale stuff. So you have to make sure that you're looking at up-to-date stuff. So I spent a lot of time working on this thing called Corona, which has come up a few times. The pole-based scheduling, in my mind, was a fundamental problem in Hadoop, and which wasn't quite getting solved in Hadoop v2 as well. So the way we re-architected the system was that just like Hadoop v2, which Raghu was asking me about, which spawned up this whole talk, we decided to separate the manager of cluster resources from this act of scheduling a job. So there's a single cluster manager in Corona, which is called a resource manager in Yarn, which is Hadoop v2, that knows about all the things that are available in the world. It's kind of like your promise manager, which knows all the retailers and all the inventory that everybody has, right? Instead of a single job tracker that schedules everything, you have one job tracker per job, right? This job tracker comes along and says, in the case of Corona, it says, I need 100 mappers and 32 reducers. And it doesn't poll. It says, look, this is my interest. Anytime you have resources that match this, you give it to me, right? Give me a call back, right? So this, completely pivots the architecture from a pull-based architecture to a push-based architecture. So now the way things work is that, let's see, do I have a slide on that? No. So the cluster manager knows that there are 50 empty things lying in the system. It says, okay, you need 100 things. Here's 50 of them, right? Go work on them. And this guy, the job tracker, immediately goes to those 50 nodes and says, here, take this and run. So you've sort of taken like 50 heartbeat pings and essentially converted them into vectorized operations where 2 or 3 steps are required to schedule 50 or 100 or 1,000 nodes instead of a linear sort of number of heartbeats in the number of nodes. Let's see. Now, I think one interesting question that I would pose to the audience, and I don't know if somebody wants to take this up, is push versus pull is actually not as one-sided as I'm making it sound. There are actually severe pitfalls to a push-based architecture, which actually, if you do not know, you will probably fall into them. So if anybody has any idea what a downside of this kind of system would be, I would love to see a raise of hands. Anybody? But we could build reliable transport layers, right? That's a kind of a solved problem. You could just keep retrying.
Right. So what happens when the this side?
Yes, Uday. A deadlock. Explain. Okay, good point. Sort of getting there. Yes. So I'll take that as sort of approximately the correct answer. I don't know. Somebody else wanted to say something? Right. So you still got to have heartbeats. So I think this argument is not for removing heartbeats, and the heartbeats have to be sort of kind of like poles. Once in a while they'll come and ping. So assume the existence of heartbeats, but the gentleman there pointed out correctly that if you're pushing stuff, and what if that machine is dead, or even worse, it's slow, and doesn't respond in time, right? It's not exactly a deadlock, but this is actually a classic problem that every person who has ever written an application has seen, right? When you write a web application and you're talking to 100 different databases, 100 different shards, if one of them slows down, ultimately all of your web services will slow down as they eventually end up talking to that database, right? So that's the downside. So we were kind of very cognizant of it when we did this project, and so we used to treat our nodes as sort of we would bucket them into partitions, and we'd have separate thread pools for talking to different subsets of nodes. So that way we would at least if one of those sets of nodes, if it was a bad node and it sort of stopped responding to these push messages, it would not slow down the entire system, but it will only slow down like some of the threads in the entire system, and you could sort of recover. So there was some amount of fault isolation. Okay. All right. So both Corona and Yarn are very scalable. We actually didn't suffer from scalability all that much because we had done fine-grained locking, but with the changes we did, it sort of became almost infinitely scalable. Corona has been in production in Facebook for probably at least a couple of years now. No, not maybe a year or a year and a half. So it's actually fully in production. There's nothing other than Corona that runs in Facebook. We're still not offering it at Qubole because we don't have as much issues with scalability yet. We're not at the Facebook scale, but we'll probably look into it. But Hadoop v2, which is Yarn, also does a lot of these things, right? It also has this separation of the resource manager and the job tracker, and it does a lot of other nice things, which I'll just go to the next slide. So when we, at least at Facebook, wrote the cluster manager in Corona, I talked about this optimistic locking pattern. We knew that this one thing we could not parallelize. It had to be like extremely performant, and so we had it was completely based on optimistic locking pattern. We wrote it very, very carefully. It's a very small, tightly controlled piece of code. Main difference in approach was that at Facebook we kind of had already solved the scalability problems because of this locking re-architecture, but we really cared about latency, and so we did a lot of stuff in Corona that was based on latency, like the push-driven event flow. One of whose main benefits is obviously it's very, very low latency because you're scheduling a lot of things very fast. Yarn, which is Hadoop v2, had slightly different goals. They saw Yarn as a way of solving the scalability problem. So instead of fixing the legacy job tracker, they said let's split up the job tracker and get parallelism to solve the in a job tracker scalability problem. And Yarn was very much interested, and rightfully so, to run heterogeneous workloads on the same compute pool. So they wanted to get away from sort of running just MapReduce and saying that we want to run all kinds of distributed processing platforms on a large Hadoop cluster. So let's go back to the reducer thing. And this is sort of one of maybe my still remaining favorite things, maybe if I had time to work on. So Hadoop 2 Yarn does remove the distinction between map and reduce slot and says that, look, we are just giving out memory, right? Because memory is something that you cannot oversubscribe. So let's just give out pieces of memory to different people who want memory. That way, at least we never have too many mappers and too many reducers. Unfortunately, it's kind of not enough, right? Because so let's say you took your 8 CPUs and say, okay, now I have 8 gigs. I'll just give out maybe 1 gig per task. I'll have equivalent of 8 slots, right? But the reducer will say that I need 8 gigs, but it doesn't really need 8 gigs for a long time. It's going to sit there for an hour and just fetch map outputs. So it's completely network bound and not memory bound and not CPU bound at the beginning of its execution. And so that means that you've again undersubscribed your system, because you've given away 1/8 of your system to the reducer, which only does network IO and no CPU. Still long running, still can't be preempted. I mean, can be preempted, but like really bad to preempt it. And so there's some, there's one of the morale of the story in looking at this whole architecture is that when you're designing a system like this, think about how to make everything that you run small, right? Whether you do it by checkpointing or whatever, like come up with some technique, but you cannot have this, large Mongo things that you run and expect to get away with it. It's not going to work. So I wish, we had an architecture where we could have lots of small reducers, and it doesn't work in Hadoop right now because of sort of lots of other reasons. But if I could run millions of small reducers, then I wouldn't have all these issues regards to much of the discussion in this talk. So a lot of it boils down to this one simple thing, and that's kind of a hard problem that's still not been solved. Okay, so in terms of where I think things are going, obviously with Yarn there's a lot of sort of work around sort of other kind of frameworks like Taze and Storm and even Spark, sort of all sort of trying to use the same set of nodes. We at Qubole are a little bit sort of looking at a slightly, obviously those things are interesting, but we see a very different aspect of this business, which is a little bit unique to the cloud. So the basic thing is that we've always, we've all been brought up in this environment where our hardware is fixed, right? So we buy 1,000 nodes with certain characteristics, so many disks, so much memory, blah, 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 right? And then we have a bunch of operations guys and stuff. We tell them, okay, look, if you have this kind of machine, this is the kind of Hadoop configuration you come up with, right? And they do that, and everybody knows, oh, if I'm going to be submitting a query, I have this much memory, so I'm going to parameterize it in this manner, right? All nice and good, except in the cloud, everything has become dynamic, right? I can get more nodes or lose nodes depending on whether it's Christmas season or not, right? Right now, spot nodes are really cheap. In Christmas, they were terribly high priced, right? Depending on what's available in the market, I can get thin nodes, fat nodes, all kinds of nodes, right? So there is no right Hadoop configuration. It is even getting impossible to come up with the right way of cutting up a task like a Hive query or some other big script into something that goes across 1,000 machines, because you don't know what those 1,000 machines are going to look like. Right? So that's a very sort of a unique aspect that we are seeing, is that this online scheduling problem is becoming an even more online scheduling problem, where more and more parameters are getting sort of unfixed and dynamic, right? And a lot of software changes are required to make the system adaptive to any kind of computation resource that gets available in the system. And I think that's it. So I'm at the end of my talk. This is me again, my contact, and I'm happy to take any questions at this point.
So there's something that I never understood clearly. So suppose there are 3 jobs running, and they depend on each other's output. So do we want to make some sort of shared memory, or how do we handle these kind of scenarios?
I mean, actually the genesis of Spark is partly in this, right? That there are iterative or dependent jobs that are all feeding off outputs of each other, and you can store them in memory. And so the fundamental focus there is on a sort of a shared memory, a substrate where you can store in-memory objects. But people have been doing this in Hadoop for a long time. I mean, obviously you can write to HDFS. People write to like Edgebase or Memcache kind of systems. So that yeah, that's my sort of first quick take on that.
Joydeep.
Yep.
Here.
Right.
To your left.
Somewhere. Okay.
Okay, somewhere.
Yeah.
So we keep hearing about speculative execution in MR clusters.
Yeah.
Right. So can you shed some light into when does it happen? Is it more for completing tasks at the cost of resources, or is it still being used when you use large clusters?
Oh, of course. In fact, the larger the cluster, the more speculation, I mean, the more important speculation becomes. So speculation is nothing but an attempt to mask failures in the system, right? Whether those are failures in the hardware, in the network, in sort of bugs in your job and so on and so forth, right? And the larger the clusters, the more the jobs you run, the more failures you will hit, which need to be masked by speculation. So that answers one part of your question. How does it work? It works by with the help of a lot of statistics in the system. So every task reports progress, and it has to be very religious in reporting that. Otherwise, speculation will not happen. And those tasks are converted into sort of distributions with mean, medians, deviations, and there is some component in the system that looks at outliers and decides that these things look like they are progressing too slow. It is those statistics themselves are very hard to cook up, because let's take an example, right? So you may have a Python application that decides to read almost all the rows and then starts working on it. So maybe it like puts it in an internal hash map or a list, and then says, I have all the rows, now I'm going to iteratively do some stuff. So the way Hadoop works, at least, is that it will consider you to have read all the rows and says, oh, you're 100% done, except you were not 100% done at all. You were just getting started. You just ingested everything into memory and then started sort of chewing on it. So it's very tricky to get this right. But those, I mean, a lot of work has gone in. This is one of the things that actually, for production users, again, I would encourage them to look at the Facebook distribution and see what we did, because actually what happened is the Apache speculation stuff actually doesn't work that well. So we made lots and lots of fixes to get it to work. I'll give you a simple example. One of the simplest things we did was, one of the guys who worked with me who came up with this, he said, you know what, Joydeep, I'm sick of dealing with the speculation problems. Every morning I get a call saying that my job didn't complete because you guys didn't speculate task number X. And task number X ran the whole night and did not finish. So you know what I'm going to do? We have a big enough cluster. I'm going to just always speculate the last n tasks in a job, right? Dumb, absolutely dumb, right? But works beautifully, because either it works, or if it doesn't, at least you can go to your consumer and say, look, we tried speculating at least. If it doesn't work, then there's a problem in your software. It's not my problem that I didn't sort of, rerun your stuff. So that's my quick take on speculation. So the statistics on Hadoop are very interesting. So as a lot of people know, Qubole, we have auto-scaling clusters. We actually drove a lot of those statistics to drive our auto-scaling algorithms, because we know exactly what every task in the system is doing, how much progress they've made, how much time is left on the clock, how much the job is supposed to take, and we used that to drive sort of provisioning and deprovisioning decisions in the system.
Joydeep, we have time for one last question.
Sure.
Hi. Here.
Yeah.
Okay. So with the 2.3 release of Hadoop, we have the cache management feature, right? So how does that affect scheduling, or is that already taken care of by the existing data structures, or is there going to be any changes to scheduling based on that? That was one question. Mm-hmm. To add another question,
sure.
I've seen articles saying Storm can now using Yarn, taking advantage of Yarn, Storm can run on the same Hadoop cluster. So how, if you could shed some light on how that gets scheduled. How Storms, the Bowls and all those, how they get scheduled, because they are kind of long running stuff, right? So
yeah, so that's an excellent question. So The first part, the caching stuff, I haven't looked at it. It's very interesting, and we've been doing a bunch of caching on our side. But I presume you would treat caching the same way as you treat data in HDFS, which is thus that certain data sets would be resident in memory on certain nodes. And when you want to schedule a compute unit for those data sets, you would prefer to go to nodes that have that data set in the cache. So you would sort of integrate the knowledge of where the cache is into your scheduling framework, and I'm sure those the Hadoop guys have already done that.
Right. How about this? Like now memory also becomes like a, like a CPU contented resource, right?
Right.
So, and there might be multiple tenants, and how do we apportion the memory?
So I'm not an operator of this piece of software. I do not know its operational characteristics, but I presume in some kind of LRU scheme would work perfectly well. If you do not find something, if you say that, oh, I think it's in memory, and you go and try to run there, and if it's not a big deal, you'll just hit disk, right? Now the second part of your question is an extremely interesting question. So as a guy who lives in the cloud, I deal with virtual machines all the time, and I don't buy this thesis of doing. You could argue that if you are running long-lived applications, why the hell would you use a brand new framework? Why wouldn't you just spin up virtual machines, right? And that's what you would do in the cloud, right? If you went to AWS and said, I had to run a strong cluster, and I had to run a Hadoop cluster, and I had to run a Spark cluster or something else, right? Then it's very hard to argue that all of them should run on the exact same underlying virtual machines, right? Because you can get virtual machines, on the fly from Amazon, right? There are some arguments, but it's a tricky argument to make. The second thing is exactly like you pointed out, that Yarn was actually not designed for long running stuff. It can do it, right? Of course, you can dole out a resource for hours and hours, but what good does that do, right? You might as well come up with a static configuration, or in this case, a provisioning of virtual machines to divide up your physical resources into reasonably statically into sort of long-term demand, and just let the system run that way. Why would you have all this complexity? So I think that there is a lot of, this new stuff in the market. Best practices will emerge. I think we are kind of not there.
Thank you.
Cool, great. Thank you so much. Thank you for having me again, and hope you have a great day.
Thanks a ton, Joydeep. It was really good to have you back again.